Welcome viewers. In this lecture we are going to discuss solution of system of linear equations. We will be using all those concepts which we have developed during my lectures on matrices. To start with, we will first discuss solution of system of homogeneous linear equations. The homogeneous linear equations can be expressed in a matrix form as Ax is equal to 0. Here A is a square matrix of order n and x is a vector of unknowns. So, we have n equations in n unknowns. Now, we call this equation homogeneous because the right hand side is 0 and all the equations are having homogeneous terms, that is all terms are involving an unknown variable x in degree 1 and there is no term which is constant, and that on the right hand side we have 0 only. So, A is a square matrix of order n. To solve this system, we first develop a theorem according to which the following two statements are equivalent. First statement says that if A is non-singular and second says that Ax is equal to 0 has only the trivial solution. By this I mean to say that if A is non-singular, then Ax is equal to 0 has only the trivial solution, or if Ax is equal to 0 has only the trivial solution, then A is non-singular. So, let us first prove this result. To start with, we prove the forward side, that is A is non-singular. By this statement I mean to say that determinant of A is not 0, this by the definition of a non-singular matrix A, and if determinant A is not 0, then the augmented matrix formed by the column vector 0, that is A colon 0, will be transformed to the matrix In colon 0, in which we will be having identity matrix on the right hand side. That means we can apply elementary operations on the augmented matrix, and this augmented matrix can be converted to a matrix like this, and this simply means that we will have identity matrix as a coefficient matrix and the right hand side is 0, and by this I mean to say that if I am having n is equal to 3 and I am having 3 unknowns x, y and z, then from this z is equal to 0, y is equal to 0 and x is equal to 0. That means 0 0 0 is the solution of this matrix. This is I have explained for n is equal to 3, but this is true for n value, for any n. So, this simply means that x equal to 0 is the solution of given system. So, I have proved this part. This is one way of proving this. Another way may be that rank A is equal to n. If determinant A is not 0, then we know rank A is equal to n, and accordingly nullity will be 0, and if nullity is equal to 0, then the system Ax is equal to 0 has the trivial solution x is equal to 0. So, we have proved that x equal to 0 is the solution of given system when A is non-singular. So, this is first part. According to the second part, B implies A, that is if x is equal to 0 is the solution of the system, then we will prove that the matrix A is non-singular. To prove this, we say that the augmented matrix A 0 can be transformed to In 0 because x equal to 0 is the only solution of the system, and this means determinant A is not 0 and this by definition A is non-singular. So, we have proved the theorem for the system of homogeneous equations. So, if the system is homogeneous, we will have only the trivial solution provided determinant A is non-zero. Now, we consider a non-homogeneous system. So, let us consider a system of m equations in n unknowns, that is Ax is equal to b, then the matrix A is of order m by n, where m are the number of equations and n is the number of unknowns. Now, we consider different cases. Case 1 is when m is equal to n, that is the number of equations is equal to number of unknowns. In that case, the matrix A is a square matrix. So, let us consider a situation when rank of A is equal to n. So, if rank of A is equal to n, that means matrix A is non-singular, and if the matrix A is non-singular, then the matrix is to be invertible. That means we can very easily find out A inverse, and A inverse exists. And if A inverse exists, then we can pre-multiply our given equation Ax is equal to B by A inverse, simplifies to x is equal to A inverse B. So, this expression gives us the solution for the non-homogeneous system Ax is equal to B. Now, this simply means that finding the solution means finding inverse of the given matrix A. So, if the solution is to be obtained, then we have to first obtain A inverse, and then A inverse multiplied by B is the solution of the given system. Now, this is actually the basis for a method developed as this method is called Cramer's rule, and according to this, a non-homogeneous n by n system Ax is equal to B, given that determinant A is not 0, then the system has a unique solution. So, this method is applicable when determinant A is not 0. The unique solution of the system is given by x1 equal to determinant A1 divided by determinant A, x2 equal to determinant A2 divided by determinant A. The ith component of the solution vector xi is equal to determinant ai divided by determinant A, and the last component xn in the solution vector is determinant an divided by determinant A. What are A1, A2, AI matrices? These are the matrices which are obtained from A by replacing the ith column of A by column B. So, let me first prove this result. So, for the given non-singular matrix A, the solution is x is equal to A inverse B. This we have just now established, and accordingly the solution vector x is adjoint of A divided by determinant A B. This is the definition I have taken for the inverse A inverse. So, x is equal to adjoint A divided by determinant A into B. Now, we can write down this equation in this expanded form. On the left hand side, I have the column vector x1, xi, xn is equal to 1 over determinant A. Then I am writing adjoint of A. This is my adjoint of A, and then the column vector b1, bj and bn. So, this is the matrix adjoint of A, where A1 1, A1 I, etc. these are the cofactors of the corresponding elements in the matrix A, and then we take the transpose. So, let us simplify this. If I write down the transpose, then the columns will become rows and rows becomes columns. So, this is what I got the transpose matrix A11, A1I, A1n in the columns now. Previously they were in rows, and AJ1, AJI, AJN they are now in columns. Previously they were in rows. So, if I perform this multiplication, then xi, if I consider the ith component here, is equal to 1 upon determinant A. This is constant, so I am writing it here. Then I will see what is the ith component from this product. So, to get the ith component of this product, this is A1i multiplied by B1, then we will have A2i multiplied by B2. So, this ith row multiplied by this column, that will give me the ith component here. So, xi is equal to this element. So, this element is obtained by multiplying this row by this column. So, it is A1i B1 plus AJI BJ, this multiplied by the jth element here, and ANI multiplied by BN. So, Xi is equal to this. To prove the result, I have to show that this is nothing but determinant AI. So, let me first simplify the determinant AI. For this purpose, let us consider determinant AI as this determinant. Now, what is this determinant? Is the determinant of the matrix A with ith column is replaced by the column B, which was there on the right hand side of equation Ax is equal to B. So, this is the column which I have replaced at the ith position. So, this is determinant AI. To simplify this, if I expand this determinant along this column, then I know AI, determinant AI is equal to A1i multiplied by Bi plus A2i multiplied by B2 plus AII multiplied by Bi plus ANI multiplied by Bn. So, this I know from the properties of determinant. So, this is nothing but determinant AI. So, once I am convinced that this is this expression of determinant AI, I can easily prove the result. Now, if determinant A is equal to 0, then since the formula which I have derived has determinant A in the denominator, the Cramer's rule is not applicable. And further, Cramer's rule is applicable for n by n system, because only then determinant A is meaningful. So, Cramer's rule has two limitations, that is, it has to be applicable for n by n system, and second, determinant A should be non-zero. So, let us illustrate the Cramer's rule for this given system. I have been given a 3 by 3 system, and it is non-homogeneous system because right hand side is a non-zero vector. So, we have to first find that this system has a unique solution. So, this involves an unknown constant A. So, the question is, for what value of A the system has a unique solution. Now, we know that the system will have a unique solution provided determinant A is not 0. So, determinant A is to be evaluated. So, to calculate determinant A, I write 3 1 4 in the first row, 0 1 A in the second row, and 1 1 2 in the third row of the determinant. So, if I simplify it, it is 3 times 2 minus A plus 1 into A minus 4, and that gives me 2, this is 6 minus 4 is 2, and minus 3A plus A, so it is minus 2A. So, determinant A is 2 minus 2A, and this will be 0 when A is equal to 1. So, this system will not have a unique solution when A is equal to 1. For all other values, the system will have a unique solution. So, the given system has unique solution when A is not equal to 1. So, this is the conclusion on the basis of this. So, we solve this system when A is equal to 0. So, I have taken A is equal to 0 in my earlier example. So, let us solve this system, and we solve this system using Cramer's rule. So, we first calculate determinant A. As you have seen, I have already computed determinant A as 2 minus 2A, and A is equal to 0 in this example. So, that gives me determinant A is equal to 2, but this Cramer rules means that I have to evaluate determinant of A1, where A1 is this matrix, and if we evaluate this determinant, then this determinant comes out to be 2. That can be very easily obtained. It is, if we expand about this particular row, then determinant A1 comes out to be 2, and determinant A is equal to 2 and determinant A1 is equal to 2. So, according to the Cramer's rule, determinant A1 divided by determinant A gives me the solution. So, x is equal to 1. 2 divided by 2 gives me x is equal to 1. For the second component, I first calculate determinant A2, which is obtained by writing the matrix A and replacing the second column of the matrix by the column vector B. So, column vector B is 2 1 1. So, I am replacing the second column by 2 1 1. So, if I evaluate this determinant about this particular row, then it is 3 into 2 minus 4, that gives me 2. So, 3 into 2 is 6 minus 4, that gives me 2, and that means y is equal to 1, because y is equal to determinant A2 divided by determinant A, which I have already computed as 2. So, it is 2 divided by 2, that comes out to be 1. Similarly, determinant A3 is computed by replacing the third column of the matrix by the column vector 2 1 1. And now, when I expand this determinant about, say, this row, then this comes out to be 1 minus 1 is 0, and from this it is 1 minus 2. So, the result comes out to be minus 1, and then from here I can compute z is equal to minus 1 divided by 2. So, z is equal to minus half. So, my solution is x is equal to 1, y is equal to 1 and z is equal to minus half. Let me check whether it satisfies the given system or not. So, to verify, I write down the matrix A and write down the solution 1, 1 and minus half. If I compute this, it is 3 into 1 plus 1 and minus 2. So, the result is 2. Then this multiplied by this is simply 1, and this row multiplied by this column gives me 1. So, 2 1 1 is the given right hand side, and this verifies that whatever solution I have obtained here, that is 1 1 minus half, is the solution of given system. So, that is how we apply Cramer's rule, and one may notice that for solving 3 by 3 system, we have evaluated 4 third order determinants. But if we have an n by n system, then we will have to evaluate n plus 1 nth order determinants. Now, this means lot of computational effort is required for solving Cramer's rule. Further, there are some limitations on the Cramer's rules, that is, the matrix has to be non-singular. If determinant A is equal to 0, this cannot be applied. Further, the matrix has to be a square matrix. So, these are some of the limitations of Cramer's rule. Now, we will discuss a general method for solving m equations in n unknowns. So, let us consider a system of m equations in n unknowns. So, we have Ax is equal to b, and for a particular case m is equal to n. So, if we take m is equal to n, then rank of A is equal to rank of A colon B, the augmented matrix, is equal to n. So, if this condition is satisfied, then in fact, if this condition is satisfied, then we say the solution, the system of equations are consistent. So, first thing is there has to be a consistency, only then we can talk about the solution of the system. Further, if this is equal to n, that means the matrix A is non-singular and the system is consistent. So, determinant A is not 0. So, this rank is equal to n means determinant A is not 0. So, non-singularity of A is there, and this implies invertibility of A, and that implies a uniqueness of solution. So, this means x is equal to A inverse B is the unique solution of the system Ax is equal to B. This is the case when m is equal to n. But suppose we have a case when m is equal to n, but rank of A is not n, it is R, which is less than n, then we may not be able to get the unique solution of the system. So, for in this case, if rank A is equal to R, which is less than n, then in fact we will be having infinitely many solutions for the given system. So now we have two cases. If m is equal to n, then we may have a unique solution when the matrix A is invertible, but if the matrix is not invertible and rank of A is less than n, then there will be infinitely many solutions possible. For example, consider a system of equations, the 3 by 3 system, the square matrix m is equal to n, and we have to see whether we have finitely many solutions or unique solution for this system. So m is equal to n, you can notice here, and then we consider the augmented matrix, that is the matrix A, the coefficient matrix is written here, followed by the column vector 6, 10, 16. We apply elementary operations on this augmented matrix, so that this and this becomes 0, and this matrix will be transformed to this matrix, which may be further transformed. See, in this case, this row is equal to this row. So if you subtract this row from this row, then we will have a 0 row in this matrix. So if you can notice that rank of A cannot be 3, the size of the system. So rank may be 2, in fact it is 2, because we have a 2 by 2 matrix which is having determinant non-zero. So this matrix has rank 2. So according to the result here, we will be having infinitely many solutions. Why? Because rank of A is equal to rank of the augmented matrix, and this is 2, which is less than 3. Then we have this augmented matrix. Then from here, this equation is not giving any information, only these two equations are to be solved in 3 variables. From here one can notice that z can be assigned any arbitrary value. Then x minus z is equal to 2 from the first equation, x minus z is equal to 2, and from the second equation y plus 2z is equal to 4. So now we have only 2 equations in 3 variables. We can assign any arbitrary value to z, let us say k, then x is equal to 2 plus k and y is equal to 4 minus 2k, and these two equations are satisfied. And that means you can give arbitrary values to k and we will be having different solutions. So as we change values of k, x and y will vary, and that means we will be having infinitely many solutions for the given system. And this is happened because the determinant of A is 0 and rank of A is 2, which is less than 3. So we have infinitely many solutions in this case. Now I consider a case when m is less than n. So previously we were considering a case when m is equal to n, or we have a square system. But suppose number of unknowns are less than, number of equations are less than the number of unknowns, then what will happen? Rank of A is equal to R, which will be less than equal to m, but this m will, since it is given to be less than n, so rank R will always be less than n. So this is the situation, and then according to the rank nullity theorem, nullity of A is n minus R, and if that is the case, then the system again will have infinitely many solutions. In fact, n minus R unknowns can be assigned arbitrary values, and only R unknowns will be written in terms of remaining unknowns. So R unknowns are expressed in terms of remaining n minus R unknowns, and this I illustrate for this system. So let us have 4 equations in 6 unknowns. So I have the coefficient matrix as this is the column vector of unknowns, they are 6 in number, and we have 4 equations. So in this system, if I consider the augmented matrix A colon B, then this is the coefficient matrix, and here I have added the column vector 2, 3, 2 and 7. I can apply elementary transformations, and this can be reduced to this. This can be done very easily. You can subtract this from this, you can subtract this from this, and then one can add the 3 and subtract. So, this can easily be transformed to this by using elementary transformations. Now, in this case one row is identically 0. You can further simplify it. So, this is what I have obtained in my last slide. One can notice that this is a square matrix which is having non-zero determinant, and that means the rank of this matrix A is 3. Further, if you consider this, then again the rank comes out to be 3. That means the given system is consistent, as the rank of A and the augmented matrix both are equal and they are 3. Now, if this is the transformed matrix, transformed augmented matrix, then one can notice that this row and this row has the leading ones in this column, the leading one here, and the leading one is here. Leading term is this in the matrix, and from this discussion we conclude that rank A is equal to 3 and we have a consistent system, and this is leading one corresponding to the unknown x1, this leading one is corresponding to the unknown x3, and this is corresponding to x5. So, we can say that x1, x3, x5 are expressed in terms of the remaining unknowns, that is x2, x4 and x6. So, we assign arbitrary values to these unknowns x2, x4, x6, and we can write down x2 as r being arbitrary, x4 as s and x6 as t. So, we have assigned arbitrary values r, s and t to x2, x4, x6, and then the remaining unknowns x1, x3, x5, they are expressed as x1 is equal to 2 minus 2r minus 3s minus t. So, from the first equation I am writing x1. So, in fact, I am using first equation for x1, and this equation, second equation is used for expressing x3. So, x3 is equal to 1 minus 2t. This is x6 and x6 is equal to t, that is what I have assigned here. So, from this equation I am getting this, and this equation is used for writing x5. So, on the right hand side we do not have any, on the right hand side we have 0 here. So, we simply say x5 is equal to t. So, this third equation is obtained from this third equation, and fourth equation is trivially satisfied. So, we have these solutions in terms of unknowns r, s and t, and as we vary r, s and t, we will be getting different values of x1, x3 and x5, and that means we will be having infinitely many solutions to the given system. So, with this we come to the last case where n is less than m, that is the number of unknowns is less than the number of equations. Clearly, even in this case rank of r will be r, and it will always be less than equal to n, because this rank r cannot exceed n. So, we will have rank A is equal to r. Now, if we have such a system, then we can reduce the augmented matrix in this form. This is reduced row echelon form, in which rank is r. So, we will be having IR here, identity matrix, and rest of the rows will be 0. Since we are having rank as r, then m minus r rows will be 0. and if that is the case, then we can assign arbitrary values to m minus r unknowns, and only r unknowns can be written in terms of m minus r unknowns, and that means we will be again having infinitely many solutions. So, we will have in this case m minus r equations which are redundant because they are zeros, and it may happen that the system is not consistent. Then of course we cannot solve the system, but if it is consistent and if r is equal to rank of a is less than n, then infinitely many solutions can be obtained. In the next example, I am considering the case when n is equal to m. So, let us solve the system in 3 unknowns when 4 equations are given. So, let us have this system, which is the coefficient matrix is 4 by 3. 4 rows and 3 columns. So, we consider first the augmented matrix, where this column is added here. So, this is the augmented matrix. We apply elementary transformations to this matrix, and first these entries are made zeros. So, this matrix reduced to this matrix, and in this matrix one may notice that 5 is common and here 10 is common. One can take 6. You can further rationalize this row, and applying elementary transformation to this matrix gives this matrix, and from here one can notice that this row is identical to this row. So, this row can be made to 0, and this matrix transforms to this matrix having one row as identically 0, and from here this square matrix has determinant non-zero. One can notice here, if you expand about this particular row, then 2 into 1. So, this is non-zero determinant. So, the rank of this matrix is 3. So, rank of this matrix is 3, which is the number of unknowns. Further, it is a consistent system because rank of A matrix is 3 and rank of augmented matrix is also 3. The consistent system, and having one redundant equation in this case. However, making this equation as redundant, we have 3 equations and 3 unknowns. This system can be this determinant is non-zero. So, this matrix is invertible, and then the solution of this matrix can be obtained uniquely. And if we solve this, then third equation gives me z is equal to 3. Substituting z is equal to 3 in this equation gives me 2 minus 3, that is y is equal to minus 1, and substituting z is equal to 3 and y is equal to minus 1 in the first equation. We call this procedure as a back substitution. We start with the lowest entry, where the value of this is substituted in this next equation, and all the values will be substituted in this equation. So, following this procedure, x comes out to be 9 minus 3 minus 2. So, this comes out to be x is equal to 2. This is minus 2, this is 3 and 3 9. So, this 9 will get cancelled with this, minus 1 and 2, that is minus 2. When it goes to the other side, x comes out to be 2. So, this system has unique solution. So, we have discussed methods for finding solution in different cases. Different possibilities are there when m is equal to n, m less than n, m greater than m. Now, we have two situations when the system is homogeneous, when the system is non-homogeneous. So, what is the relationship between the system of a homogeneous system of homogeneous equations and system of non-homogeneous equations? For this purpose, let us say xp is a solution of non-homogeneous system, Ax is equal to b, while xh is the solution of corresponding homogeneous system, Ax is equal to 0. Then one can prove easily that xp plus xh is also a solution of non-homogeneous system, Ax is equal to b. One can very easily check it. If we substitute xp plus xh in this equation, then this equation must be satisfied. So, for this purpose I write A, and in place of x I write xp plus xh. Perform this multiplication, it is axp plus axh, but axh is equal to 0. So, what remains is axp is equal to b, but we know that xp is a solution of ax is equal to b. So, this equation is satisfied, and that means xp plus xh is also solution of ax is equal to b. Now, this is very similar to what we have in case of differential equations, and we have a result that every solution of ax is equal to b can be written as xp plus xh. So, it has two components, one is the solution of homogeneous part and this is the solution of non-homogeneous part. We call it xp is called as a particular solution. So, if we represent the solution of ax is equal to 0 on the plane, see, for ax is equal to 0, 0 0 is also a solution, then we may have solution number of solutions other than x is equal to 0 if determinant A is 0, then possibility of other solutions are there, and we know that all these solutions of this equation, they will form a vector space. So, I am denoting that plane consisting of all the vectors which satisfy this equation as this plane. So, this plane means the solution of all the solutions of Ax is equal to 0. But if I consider Ax is equal to b, then this plane will be parallel to this plane, and all the solutions here, they are shifted this distance, they will form a solution of Ax equal to b. That is the relevance of xp plus xh. So, the solution, these two planes are parallel planes. So, this is the geometrical interpretation of xp and xh. Now, we have discussed number of results related to the two systems Ax is equal to 0 and Ax is equal to b. Now, we say that the following statements are equivalent for a square matrix of order n. So, the first statement is A is non-singular, second is determinant A is not 0. We are in fact using this definition for a non-singular matrix. Then A is row equivalent to In. Whenever the determinant A is not 0, then we can always reduce A to In by applying elementary row transformations. A has rank n, determinant A is not 0, so rank will be n. A has nullity 0 due to rank nullity theorem. The rows columns of A form a linearly independent set of n vectors. This also we have proved earlier. And finally, Ax is equal to 0 has only the trivial solution. So, all these statements are equivalent related to Ax is equal to 0. Similarly, the following statements are equivalent when we have A is non-singular, determinant A is not 0, all these things are same which we have discussed. The last point is slightly different, and it says that the system Ax is equal to b has unique solution for every column vector b. So, we have X is equal to b non-homogeneous system, it will have a unique solution for every column vector b if matrix A is non-singular or determinant A is not 0 or A is row equivalent to In or A has rank n or A has nullity 0 or the rows of A or columns of A form a linearly independent set of n vectors, then the system Ax is equal to b has unique solution for every column vector of b. Now, with this we have arrived at the end of this lecture, and in this lecture I have discussed different situations for solving system of equations. We may have a homogeneous system of equations or we may have non-homogeneous system of equations. If it is homogeneous system, then we check the determinant, and accordingly we say that whether we are having the unique solution or we can have a trivial solution or we have infinitely many solutions. Similar cases we will discuss for Ax is equal to b when we have 0 solution, when we have unique solution, when we have infinitely many solutions. So, all these cases we have discussed for solution of system of equations. Thank you.